We, as physicists, have been anticipating this moment for an entire century. It all started around 1916 when the first theoretical concepts emerged regarding black holes, which are now considered to be one of the most captivating yet perplexing features of the cosmos. These objects are enormous in terms of gravitational influence, but, paradoxically, remain almost intangible to us. A black hole, for example, may possess a mass between 2 to 4 million times that of our Sun. Over the past few decades, particularly in the last 20 to 30 years, our understanding of these celestial bodies has evolved drastically. We have gone from virtually knowing nothing about black holes to gaining progressively more insight into their complex nature. Things have only grown more exciting recently, with a remarkable breakthrough. New findings, particularly by Michio Kaku, now indicate that we have finally seen what lies within a black hole. This discovery offers valuable clues and could reveal crucial details that the scientific community may have missed earlier on. So, let's dive deeper into the mysteries of black holes and uncover their hidden secrets. The universe is vast and awe-inspiring, yet black holes continue to intrigue us with their terrifying nature. But what exactly are black holes? Before delving into the specifics of Kaku's discoveries, we must first explore the basics of black holes. While most of us have some understanding of what black holes are, there remain gaps in our knowledge. The idea traces back to 1916 when Albert Einstein presented his theory of general relativity, which predicted the existence of black holes. However, at that time, black holes were entirely hypothetical. It took another 5 decades for scientists to find solid evidence confirming their existence. This pivotal discovery occurred during the 1960s when researchers, studying a star labeled X1 in the constellation Cygnus, noticed something extraordinary: a star emitting X-rays that seemed to originate from an unseen object. Upon closer inspection, it became clear that these X-rays weren't just moving aimlessly. They were being drawn into a massive, invisible body. This marked the discovery of the first black hole, aptly named Cygnus X1. This discovery was monumental as it provided concrete evidence that black holes weren't just figments of Einstein's imagination. It opened the door to a whole new realm of cosmic study. Scientists around the world were quick to turn their attention to black holes, determined to understand this strange, mysterious phenomenon. Cygnus X1, located about 6,000 light-years from Earth, is significantly brighter than the Sun and has an incredibly dense core, giving it immense gravitational power. This gravitational force is so powerful that even light cannot escape it, which is why it's termed a black hole. The concept of a black hole is both fascinating and frightening. Essentially, it is a region in space where gravity is so intense that not even light can break free from it. Anything that gets too close to this region will be drawn in, never to escape. The mere existence of such an object makes it all the more imperative to study and comprehend every possible detail. Was Cygnus X1 the only black hole we would find, or were there more? It turned out that the latter was true. Following the discovery of Cygnus X1, scientists began searching for additional black holes, and they speculated that there might be as many as 100 million such objects in the Milky Way alone. However, identifying them remains an enormous challenge, and we still don't have an accurate count. Within our own galaxy, it's believed that there could be millions of black holes, which makes their study even more crucial. Let's break things down further. The defining feature of black holes is undoubtedly their gravity. Their gravitational pull is so intense that anything within its reach gets compressed to the point of becoming a singularity, a point of infinite density. In simpler terms, black holes function like gigantic vacuum cleaners, sucking up everything in their path. One of the most terrifying aspects of black holes is that if a person were to fall into one, they would gradually be stretched and compressed into a singular line, a process that would take place so slowly that the person would likely die before the ultimate breakdown of reality occurred. This terrifying aspect makes it clear that no one should attempt to enter a black hole. But are we in any danger? Even though the nearest black hole to Earth is nearly 500 light-years away, the very possibility of their existence raises questions. In 2021, scientists made history by capturing the first clear photograph of a black hole, specifically the one in the M87 galaxy. The photograph was the result of a multi-night effort, and as the researchers pieced the images together, they discovered fascinating insights about the structure of black holes. Through their work, researchers confirmed that a black hole isn't just an endless void but consists of 3 distinct layers. Many people mistakenly think of a black hole as a simple, singular hole, but the reality is far more complicated. To even reach the nothingness at the center of a black hole, An object must first pass through two other layers. The first layer, known as the event horizon, represents the final boundary. Once something crosses the event horizon, there's no turning back, and it is inevitably drawn into the black hole. Beyond that lies the second layer, known as the photon sphere, where light itself orbits the black hole. Any light that enters this region cannot escape because of the black hole's immense gravitational pull. Finally, at the heart of the black hole is the third layer, the singularity. Here, everything that has entered the black hole is compressed to an infinitesimally small point, causing the laws of physics to break down. We can't predict what happens next. What makes studying black holes even more challenging is the fact that no two black holes are identical. While they all tend to follow this three-layer structure, each black hole operates in its own unique way. In many cases, black holes are studied indirectly by observing the radiation they emit and the gas and dust that surrounds them. It's impossible to send a probe directly into a black hole because anything that crosses the event horizon is immediately pulled into the singularity, where it is crushed down to an infinitesimally small point. Therefore, sending a probe on a multi-billion-dollar mission to approach a black hole is a futile endeavor. Anything that ventures too close will be pulled into the black void. Given these challenges, scientists have had to adopt a two-dimensional approach to studying black holes, despite their three-dimensional nature. Additionally, the uniqueness of each black hole and the fact that the laws of physics break down when studying their interiors adds another layer of complexity. Nevertheless, scientists are not sitting idle. Numerous theories and explanations regarding the formation and behavior of black holes have been proposed. One of the most compelling hypotheses is that black holes form from collapsing stars. When a star exhausts its nuclear fuel, it can no longer generate enough energy to counterbalance the inward pull of gravity. This causes the star to collapse, contracting and becoming denser with each passing moment. If the star is massive enough, this collapse continues until the object forms a singularity. To understand black holes more thoroughly, NASA focused its attention on the heart of the universe, the M87 galaxy. Astronomers observed a powerful whirlpool of superheated hydrogen gas spinning at speeds of 1.2 million miles per hour. The intensity of this spinning gas should have caused it to break apart, but scientists realized that there must be a colossal mass at the galaxy's center to prevent this from happening. This mass, which weighs as much as 2 to 3 billion suns, must have been a black hole. However, this explanation doesn't capture all possible theories about black holes. In 1963, New Zealand mathematician Royer used Einstein's equations of gravity to develop a new model of a rotating black hole. According to this model, instead of collapsing into a point, a rotating black hole would form a ring of fire or a thin disk that spins at such high speeds that outward forces keep it from collapsing. This spinning disk of matter is called the ergosphere, a region where the laws of physics begin to break down. Even more intriguing, Royer's model suggested the existence of an Einstein-Rosen bridge, better known as a wormhole. This hypothetical structure would serve as a shortcut through spacetime, potentially linking two distant regions of the universe or even two separate universes. The idea is that, instead of being crushed into oblivion, anything falling into a black hole could travel through the ring of fire and emerge out of a white hole into another universe or time. To grasp how this works, we need to consider the concept of spacetime. According to Einstein's theory, the reality we experience is not made up of separate elements, but rather forms an interconnected four-dimensional fabric. Objects with mass bend this fabric, creating gravitational fields that cause other objects to move toward them. If you imagine spacetime as a piece of paper, placing 2 points on the paper and connecting them with a line demonstrates how objects move through spacetime. But what if you could fold the paper in half, creating a shortcut between those 2 points? This represents the idea of a wormhole, a passage through spacetime that connects two distant points instantaneously. Although wormholes are theoretically possible according to general relativity, no one has ever observed one directly. The reason is that wormholes are inherently unstable and would collapse before they could be traversed. Nevertheless, the possibility of wormholes and black holes serving as gateways to other regions of spacetime is a fascinating concept. Could they allow us to travel across vast distances, or even venture into the past? Unfortunately, the answer is likely no. Not yet. Even if we could stabilize a wormhole, it would not necessarily allow us to travel faster than light, as Einstein's theory of special relativity sets the speed of light as a hard limit for any object moving through spacetime. Still, the idea that black holes could serve as pathways to other parts of the universe or even other times has sparked much debate and speculation among physicists. One of the most intriguing possibilities is the CR wormhole, named after Royer, which is essentially a theoretical tunnel connecting two distant points in spacetime. This wormhole would be ring-shaped and could potentially transport a traveler to another universe or a different time, where the laws of physics might be vastly different from those we know. While the idea of traveling through wormholes is certainly exciting, it's also a topic of ongoing debate. Some physicists argue that the extreme radiation and subatomic forces surrounding wormholes make them difficult, if not impossible, to traverse. Others point out that Einstein's equations, which are used to describe black holes and wormholes, only account for gravitational forces and do not address the quantum forces that govern radiation and subatomic particles. To truly understand the nature of black holes and wormholes, a new theory is needed, one that can unite the laws of gravity with the quantum theory of radiation. This is known as a theory of everything, a unified theory that would reconcile Einstein's theory of gravity with the quantum theory that governs the behavior of particles at the smallest scales. One of the most promising approaches to this theory of everything is the superstring theory. This theory suggests that the fundamental building blocks of nature are not particles, but tiny vibrating strings. Just as different musical notes correspond to different vibrations of a violin string, different particles correspond to different vibrations of these superstrings. Superstring theory not only unifies gravity and quantum mechanics, but it also offers explanations for phenomena like black holes, wormholes, and other mysterious cosmic phenomena. However, there's a catch. The extra dimensions of spacetime that superstring theory predicts are so small that they are undetectable with our current technology. Nevertheless, this theory represents one of the most exciting possibilities in our quest to understand the universe. Superstring theory, while promising, still remains largely theoretical and presents challenges when trying to detect its predictions. These additional dimensions of spacetime, predicted by the theory, are so minuscule that current scientific instruments are unable to observe them directly. This makes it a daunting task for researchers who are eager to confirm the theory's validity through empirical evidence. However, the theory provides a comprehensive framework that could explain many of the phenomena we encounter, such as the existence of black holes, wormholes, and even the nature of gravity itself. One of the most compelling aspects of superstring theory is its potential to resolve some of the most puzzling questions about the universe. For instance, it offers a possible explanation for how the seemingly contradictory forces of quantum mechanics and general relativity could coexist within a single framework. This is essential because, while general relativity describes the force of gravity on a large scale, such as the movement of planets and the behavior of black holes, quantum mechanics governs the interactions of particles on the smallest scales. The two theories have been remarkably successful in their respective domains, but they have never been reconciled. Superstring theory seeks to bridge this gap by proposing that the fundamental constituents of reality are not individual particles but tiny, vibrating strings.